Good afternoon, class. We are looking at Calculus 1 Exam 3. Here's the synopsis of that, covering Chapter 4, Applications of Differentiations. Exam 3 goes from 3.9 to 3.11, 4.1 to 4.5. And here's Part 1, 3.9, related rates. So what we cover, 3.9 related rates, 3.10 linear approximation and differentials, 3.11 hyperbolic functions. That finishes chapter 3. In chapter 4, we go to applications such as max and minimum values, the mean value theorem, how derivatives affect the shape of a graph, indeterminate forms of L'Hopital's rule, and L'Hopital's rule, summary of curve sketching. Here's the synopsis of the differentiation formulas from the definition to basic differentiation involving exponential sinusoidal functions and log functions and the chain rule here. And then we go to sine inverse, the product rule here, the quotient rule, so on and so forth, and the definition of an E that was discussed in the beginning. So what is related rates? Here's a simple example to get the concept going for us. So if we are pumping air into a balloon, both the volume and the radius of the balloon are increasing and the rates of increase are related to each other. But it is much easier to measure directly the rate of the increase of the volume than the rate of increase of the radius. In a related rates problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity, which may be more easily measured. So what is the procedure? The procedure, first we find an equation that relates the two quantities, and then we use the chain rules to differentiate with respect to time. And so what is the independent variable? It's a t. So in Leibniz's notation, dy dt is dy du du dt. That's the concept. Could somebody read this question?
A spherical balloon is deflating, losing 8 centimeters cubed of air per minute. At the moment when the radius of the balloon is 20 centimeters, how fast is the radius decreasing? Hint: V equals 4/3 pi r cubed.
Perfect. Now, this is a piece of information from geometry. The volume of a spherical shape is 4/3 pi r cubed, and we should know that. So that piece is from prior knowledge of mathematics. What is given, the moment you see the concept of a rate here, that means differentiation. So this is dv dt, and when it's deflating or losing, that means negative 8 cubic centimeters per minute. And so what are we looking for? So we want to translate this. At the moment when the radius is 20 centimeters, when r is centimeters, how fast is the radius decreasing? We want dr dt. So therefore, this whole question becomes translated as follows. This is a piece of information from geometry that you should have. dv dt is negative 8 cubic centimeters per minute. dr dt is missing. At what point we are interested in finding that? The value, the numerical value at the moment that r is 20 centimeters. So what we are going to do, we are going to differentiate this with respect to t, because in related rates, the only independent variable is t. So when we want to differentiate that, dv dt 4/3 pi is a number and it doesn't change. R cubed is the only variable, and when we differentiate that is 3r squared. since it's a function of t by the chain rule times dr dt. So r cubed gives you 3r squared dr dt, and it simplifies to 4 pi r squared dr dt. And all you have to do, replace the dv dt with -8 and r with 20. So this is 400 times 4 is 1600. So we're going to divide both sides by 1600 pi. 1600 pi. 8 cancels out the 16. 16 changes to 2. So dr dt is -1/200 pi centimeters per minute. And it's important to notice the units will work, meaning if you look at this one, the units of volume over the units of time. If you look at this one, the units of the radius over the units of time. Even furthermore, if you go here, this 20 is 20 centimeters that is being squared. dr dt is found accordingly. So the units, whatever we do to numbers, we do to units. This is the exact answer. And of course, you can use a calculator with a bunch of decimals. I highly recommend in your PDF file, you put your exact answer. And if they ask you for however many decimals, you do the rounding accordingly. Could somebody read this, please?
A 20-foot ladder leans against a building. The base of the ladder slips away at a rate of 2 feet per minute/minute. Find the rate of change of the height of the ladder when the base is 12 foot from the building.
Perfect. So anytime we do word problems, it is important to have the setting, the drawing. So let's see how it looks like. So here's the wall, the building, here's the ladder. It's moving away from the base and creates this situation. It's important to understand the length of the ladder is fixed, capital L, which happened to be 20 feet. So that doesn't change. As X moves to the right, Y moves down. The ladder has a fixed length of 20 feet. You can call it L, you can call it C. And as it moves to the right, it creates a speed of dx dt 2 feet per minute. We are interested in finding dy dt. At what point? When the base is 12 feet from the building, when x is 12 feet. Now, one formula we should know, it's Pythagorean theorem that says a squared plus b squared equals c squared. Everybody remembers that? In which case becomes x squared plus y squared equals 20 squared. So dx dt is 2 feet per minute. X squared plus y squared equals 20 squared. This is Pythagorean theorem. Dy dt is missing. We are interested in finding that numerically at the precise moment when x is 12 feet. So this setting, along with this line, is the translation of the question. You have to have this setting anytime you do word problems. related rates or word problems. So let's see what is the process of finding the answer. Here's the relationship, x squared plus y squared equals 20 squared. And we are going to differentiate both sides with respect to t. This becomes 2x dx dt. It's important to know the derivative of x is no longer 1 because the independent variable is t, 2x dx dt, plus 2y dy dt equals 400, 20 squared or 400 or any other number, the derivative is 0. And as you can see, we have everything here to plug in with the exception of y. So at the moment when x is 12, we can know what is the y value from Pythagorean theorem. So x squared and y squared, they add up to 20 squared. This is 12 squared. $144. This is 20 squared or 400. I thought I put 400. Subtract it from 144 and take a root, y becomes 16. And now, because it's 256. And now we have everything we're going to plug in. We're going to replace the x with 12, the x dt with 2. We're going to replace the y with what we just found to be 16, and the missing dy dt can be handled. 2 times 2 times 12 is 48. 2 times 16 is 32. We are going to move the 48 to the right, becomes negative 48. And we are going to divide by 32. And when we do that, it becomes negative 3/2 feet per minute. The units will always work, and you must answer every word problem with the proper units if units are given. Notice, x is increasing, dx dt is positive. Y is decreasing, dy dt is negative. We're going to repeat the same question, but this time we are interested in finding the rate of change of the angle between the ladder and the ground. So what happens as the move takes place, as x moves to the right and y comes down, it creates the situation that this angle changes, so does this angle. Both angles, this one changes, this one changes. Now, which one are we interested in? Find the rate of the change of the angle between the ladder and the ground. So this is the one. This is the one we are interested in. So we are interested in when dx dt is given to be 2 feet per minute. And of course, this is 12 feet from the building. We are interested in finding d theta dt. D theta dt. So we are going to write the same writing as the previous page, except d theta dt is of interest to us. We need this also since it's been done from the previous pages. Not that big of a deal in case you didn't write it, but we need that because we want the value of y, although it's been calculated from the previous page. But if it happened to be a question from the scratch. So a couple of things we need to know from trigonometry. If you look at theta, sine theta is the opposite, y over the hypotenuse 20. Cosine theta is the adjacent x over the hypotenuse 20. So sine versus cosine. And let's write both of them. This is x over 20. This is y over 20. Granted, we calculated the value of y in the previous example, but x is known. Therefore, we're going to start with this. You can use any of those formulas because it connects the missing value with the given. Now, we don't have the x dt, but the y dt can easily be found from the previous page. We're going to stick with what we have. So we're going to stick with this formula. So if cosine theta is x over 20, we are going to differentiate this both sides with respect to time. Before I do that, I want to remind you this means 1 over 20 times x. In other words, this is just a coefficient. So the left side, cosine, the derivative is negative sine. So negative sine of the same argument, namely theta, d theta dt, because the independent variable is t. So negative sine theta, and then d theta dt, because the independent variable is t. On the right side, we have 1 over 20 times x gives us the x dt, dx dt. And so you can replace everything accordingly. So minus sine theta. Okay, so minus, we know sine is y over 20, and y, we remember it's 16 from the previous page, or just recalculate it. So in this formula, I'm going to replace the y with 16, and don't forget the negative sign on the right side. So d theta dt, that's what we are looking for. On the right side, we have 1 over 20 already. We're going to replace the dx dt with number 2. And basically, you want to solve that. So to solve this, I can just drop the 2. So the left side is negative 16 d theta. The right side is 2. If you divide both sides by, let me just write this for you so it becomes clear. So we have negative 16 d theta equals 2. So divide both sides by negative 16. And you get negative 1 over 8 radians per minute. I want to explain the units. As you remember, this was per minute, so it's still per minute. But what about the units for, say, units of the numerator over the units of the denominator? The units of the numerator, when it comes to calculus, you always use radians for the measurement of angles unless otherwise mentioned. So negative 1 over 8 radians per minute. Radians per minute. Could somebody read this, please? Anyone?
I'll read it. Falling sand is forming a cone-shaped pile. The volume of the cone is increasing at a rate of 54 pi inches cubed minute. The height of the cone is twice the radius of the base. Find the rate at which the radius changes when the radius is 6 inches.
Perfect. So again, let's look at the general concept. Here's a cone, the radius r, the height h, and a piece of information again from geometry or algebra. The volume of a cone is 1/3 pi r squared h. We should have this information. Now, so we have this formula. let's write everything is given. The very first thing we see, the volume is increasing at this rate. The moment you see rate or per minute, per week, per unit of time, we are dealing with related rates. This is dV dt, dV dt. This is the volume. dV dt is 54 pi inches cube over minute, or cubic inches per minute. The height h is equal to 2r. H equals 2r. Find the rate at which the radius changes. Find dr dt. At what point? When r is 6. So the translation of this question, the volume is 1/3 pi r squared h, because we are interested in the relationship between the volume of this cone and its radius. dV dt is 54 pi cubic inches per minute. H is 2 times r. dr dt is of interest to us at a precise moment when r is 6 inches. Now, because h is 2r, we're going to replace that. Before we move on, I want to make sure everybody understands that this has two variables, r and h on the right. If you were to differentiate it the way it is, it ultimately requires the product rule. That's not what we are going to do. We are going to replace the h with 2r because we want dr dt. If for the sake of argument they were asking for dh dt, then you would replace the r with h over 2. So right now, the very first step is to replace the h with 2r. And that gives us 2/3 pi r cubed. Now, the volume is a function of a radius and radius only. We're going to find dV dt. And that is 2/3 pi. 2/3 pi is a number, everybody. And I put that on purpose. Times, now r cubed gives us 3r squared dr dt. r cubed gives us 3r squared dr dt. Number 3 cancels out this 3. We get 2 pi r squared dr dt. So dV dt can be replaced by 54. 2 pi r squared, r can be replaced by 6 and then square it. And dr dt we will find. So let's replace the dV dt by its value 54 pi. Let's replace the r by its value 6. And as you can see, this is 36 times 2 pi gives us 72 pi dr dt. We are going to divide both sides by 72 pi. Obviously, the pi's go away, and 54 and 72, they can simplify to 3/4 of an inch per minute. 3/4 of an inch per minute. So when the volume is increasing at that rate, the radius is increasing at the rate of 3/4 of an inch per minute at the precise moment when the radius is 6 inches. Word problem setting is important. Could somebody read this question, please?
At noon, ship A is 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 o'clock p.m.?
Perfect. So again, we have a word problem. There is a setting we want to discuss. We want to make sure everybody understands what's going on. So we're going to start from the get-go. At noon, the distance between the two is 150 and the units kilometers, 150 kilometers. So here's the situation we have. At noon, A sub 0, this is the initial value or initial placement of A, ship A, and this is north, okay? And here's where initial value of B, the second ship is. And we know A is moving this way, B is moving that way, right? A is moving east, B is moving north, and they have a distance of 150 to begin with, which is going to be changing because we are moving in this direction, right? So that's the initial condition, if you will. So what happens? A is going to move to the right or east. B is going to move up or north, and the speeds are as follows. A is doing 35 kilometers per hour, and B is going to do 25 kilometers per hour. So here's the initial location. It's moving. That's the A ship, it's moving. And that's the B ship, it's moving up. A moves east at 35 kilometers per hour. And we let X be the distance that it has moved. And B moves north at 25 kilometers per hour. And we let the Y represent the distance at any moment, at any time, T. So what it creates is the following situation. So we have moved from here to here. We have traveled X amount, that means X for A, and the B has traveled this, the Y amount, and the total distance originally was 150 kilometers. So if this is covered by A, of course, dx dt is 35, dy dt is 25, those are the speeds. And if this is X and the total distance is 150, then the distance remaining for this part is 150 minus X. That's why if you don't have the setting, if you don't have the variables X and Y defined clearly for your reader, if you start getting to the formula without writing those, it makes no sense. And one wonders where it comes from. So let's write now dx dt is 35 kilometers per hour, dy dt is 25 kilometers per hour, and t equals 4 because at noon till 4 p.m. there are 4 hours. The time is 4. At t equals 4, we want dz dt. This one we can call it, if this is X, this is Y, you can call it D or Z. I rather call it Z. So let's say Z. So what is the formula? We know Pythagorean theorem says A squared plus B squared is equal to C squared. So this distance, which is 150 minus X squared, plus this distance, which is Y squared, is equal to this distance, D or Z squared. Let's go with Z because we are using X and Y. And so when we do that, we are practically done because we have to differentiate this with respect to T or time. That's the main thing, setting up, coming up with the proper equation. So let's differentiate with respect to time. This one, the exponent becomes the coefficient, 2 times the same thing to the power of 1, and times the derivative of the inside, which is negative dx dt plus y squared 2y dy dt equals z squared equals 2z dz dt. So we are going to plug everything in accordingly to see what happens. Now, what are we plugging in? Well, we have dx dt, dy dt, but what is x, what is y, what is z? So now we go to basic formula d equals RT at 4 p.m. X is 4 times dx dt, 4 times 35. At 4 p.m., y is 4 times 25. So at 4 p.m., x is 4 times 35 or 140. Y is 4 times 25 or 100. What about z? Well, again, look at a squared plus b squared equals c squared, meaning look at this formula. Now we have x, 140. Now we have y, 100. So this means that 10 squared, which is 100, 100 squared, which is 10,000. They add up to 10,100. So z is the square root of that precisely. Again, let me just write that. So this is 10. So the left side is 100 plus 10,000. And z is the square root of that precisely. You use a calculator for a rough value and however many decimals. Now let's replace the values. So we're going to replace the x with 140 minus 35 plus 2 times y 100 times dy dt, which is 25, 2, and instead of z, let's put the exact answer for now. Okay. So this is 10 with negative 35. The product is negative 350. And then 2 times 100 times 2500. By the way, I'm just dropping the 2's from both sides. You can't drop it. So you can factor out the 2 from both sides. And so this ends up being 2150 divide by the square root of 10,100. And if you use a calculator now, about 21.4 kilometers per hour. 21.4 kilometers per hour. I hope you realize solving it is really not too bad as long as we go through the process of explaining the whole situation with the drawing so it becomes clear as to what we are doing. Could somebody read this, please?
I can read it. So, a spotlight on the ground shines on a wall 12 meters away. If a man 2 meters tall walks in front of the spotlight towards the building at a speed of 1.6 meters per second, how fast is the length of his shadow on the building decreasing when he is 4 meters up from the building?
Excellent. So again, we have to do the setup. We have to define variables. So here's what's happening. Somewhere we have the spotlight, somewhere here we have the wall, and this distance is 12 meters, and we are moving this way. And that creates some distance of x. The difference here is 12 minus x. And here's the setup. So here's the light, here's the wall, here's the man, 2 meters tall. This is 12 meters away. And we want to know how fast is the length of his shadow on the building. So this one is decreasing when he's 4 meters from the building. That means this distance. And what is this distance? 12 minus x. So when 12 minus x is 4. So let's do the following writing. When the man covers x amount, x feet, its speed is dx dt, which is 1.6 meters per second. We are interested in dy dt, the change in y, dy dt, the rate of change of y. At what point? At a precise moment when this distance, 12 minus x, is 4 meters. Take a look at this one. We want to make sure we understand why this is not x, this is 12 minus x. Because it says, how fast is the length of his shadow on the building decreasing when he is 4 meters from the building? And if we let this be x, this distance is 12 minus x. So we write this. So the x dt is 1.6 meters per second. The y dt is missing. And at the precise moment of 4 meters from the building, that means 12 minus x equals 4. That means x equals 8. At the moment that x equals 8, we are interested in finding the y dt. Now, this is pretty simple. We are dealing with two triangles, this one and this one. And they are similar triangles, which means we can write the ratio of, for example, this ratio to the total is this ratio to the total, just as an example. I hope everybody remembers similar figures, okay? So if I am comparing the two triangles, one way to write it, the ratio of y to 12 is the ratio of 2 to x. So this is the easiest way to involve both of them. So from the big one, y and 12, then in front of y we have 2, in front of 12 we have x, and all we have to do, solve for y and differentiate. To solve for y, I'm going to multiply both sides by 12. I get 24 over x, or 24x to the power of -1. As long as we do this drawing and writing and consider the similar figures, pretty much the rest of it is very simple. Similar figures, we should be able to figure this out. Y is 24 over x, or 24x to the power of -1. So if I want dy dt is 24 times -1. So let's do it right underneath, and then right. So I can write dy dt is 24 times -1 times x to the power of -1 or -2. And we would be done if x was the independent variable. It's not. Therefore, dx dt. And we rewrite it as -24 over x squared dx dt. And we replace the x with 8 and dx dt with 1.6. I want to make sure x is given, dx dt is given. Let's replace it. We end up with -0.6 meters per second. You can do this simplification For example, you can drop one of the 8s. This becomes -3. If you assume this is 16, this is 8, you get 2 here, but since it's 0, it's 1.6, you get 0.2 times -3 is -0.6 meters per second. The negative indicates decreasing. So the length of his shadow, the way you would answer it, because it's asking it mentions decreasing, then you answer the length of his shadow is decreasing at a rate of 0.6 meters per second. So negative indicates decreasing. When you do the writing, you don't put a negative sign here. So because x is getting larger, dx dt is positive, but y is getting, as we get closer and closer to the wall, the shadow gets smaller, y is getting decreasing, y is getting smaller, therefore dy dt is negative. Could somebody read this, please?
I'll read it. A cylindrical tank with radius 10 meters is being filled with water at a rate of 7 meters cubed per minute. How fast is the height of the water increasing? Draw a graph to include units.
Excellent. Again, even if they don't mention this, you really have to do that. I can't emphasize this enough. And even if they don't mention that, anytime you're dealing with word problems, if units are given, you have to answer with the proper units. And so here's a cylindrical shape, and the radius happen to be fixed at 10 meters. So the concept is the radius is given and is being filled with the water at a rate of 7 cubic meters per minute. So the volume is increasing in essence, right? This is rising because the volume of the water is increasing. So you have to be able to relate the volume to all of this. So the volume is pi r squared h. You should know that where dv dt is 7 cubic meters per minute, r is fixed. R is fixed at 10 meters, and we want dh dt. So the volume, this is a formula from geometry, algebra, trigonometry, you name it. dv dt is given 7 cubic meters per minute. R is fixed at 10 meters, or doesn't change because it's a cylindrical shape. And how fast is the height increasing, dh dt, or changing? By the way, they might say changing, and if it ends up being positive, that means increasing. If it's negative, that means decreasing. So as long as we have this setup, it becomes very simple to finish the job. Now we want to differentiate this. We want dv dt, pi is a fixed number, so is r at 10. You can keep those two. So dv dt becomes pi r squared, because those are numbers, times dh dt. And now we're going to replace all of them. Again, the reason this is not changing, it's fixed at 10. So dv dt, replace it with 7. Pi, keep it. R, replace it with 10. And so obviously this is 100 pi divided by 100 pi, and dh dt is 7 over 100 pi meters per minute. And this is an exact answer. That comes, okay, or class, you can go with that formula and replace the r with 100. By the way, lowercase r or uppercase r makes no difference. What I did, I like to keep it with r and then change it. You can right away notice that since r is 10, replace it. And then if you differentiate, you come up with the same answer. And if you plug in, and I'm going to keep it as an exact answer. I'm going to write at top of it, class. This is an exact answer. But if they ask you for so many decimals, you follow 7/100 pi meters per minute. As always, the units of volume over the units of time, the units of height over the units of time. The units will always work. You want to follow that. If the minute hand of a clock has length r, it happened to be in centimeters, we want to find the rate at which it sweeps out area as a function of theta. This is the general question, class. So first, we are looking at a circular shape. Here's the radius. Here's the angle that it sweeps, the theta. And we are going to write the information. So the minute hand has length r, and we want to find the rate at which it sweeps out the area. So it moves and it goes so much, and it covers this area of a sector. You remember the formula from trigonometry, 1/2 r squared theta, and the ADT is of interest to us, where r is just obviously a fixed number that is not changing. R is not a variable. It is the angle that is varying. And I'm going to remind you that if you recall, the area of a circle, right, is pi r squared. You could write it as 1/2 times 2 pi r squared. Remember, when we start from any point and we go around the circle, we cover 2 pi radians, right? So from any point all the way around, you cover 2 pi radians. So if you happen to cover something less than that, let's say theta, the formula becomes 1/2, see 1/2 r squared, replace the 2 pi with theta. Replace the 2 pi with theta. If theta is 2 pi, is the area of a circle. This, in essence, this is the proof of the area of a sector. I remind you from trigonometry. So this area. By the way, just in a related concept, this distance, if you recall, S is r theta. Anyways, all right. So now we want the ADT, which is differentiate this 1/2 r squared. This is fixed. This is a coefficient. Just theta gives you d theta dt. And that's all there is to it. That's all they're asking. So for example, if it's 1 hour, meaning 360 degrees or 2 pi over the course of an hour, 2 pi, then 1/2 r squared times 2 pi gives you pi r squared, and the units of the area over the units of time, units of the area over the units of time. So pi r squared, centimeters per square per hour, just as an example. Again, this is the end of the story as far as we are concerned. Could somebody read this one? The last question. Last question, anybody?
I'll read it. A streetlight is mounted at the top left of a 15 feet tall pole. A man 6 feet tall walks away from the pole with a speed of 5 feet per second along a straight path. How fast is the tip of his shadow moving when he is 40 feet from the pole?
Perfect. So it's important to understand the setup and the drawing. So when the man covers X amount, we say the shadow covers Y amount in this format. So the man covers X amount, the shadow is covering Y amount. This is the tip of man's shadow. The man is 6 feet tall, starting from here, 15 feet pole. Here's another way of putting it. 15 feet pole, 6 feet, that's the height. And the man is moving at dx dt or 5 feet per second. How fast is the tip of his shadow moving? When he is 40 feet from the pole, when the distance from the pole. Now, it's important to see what is given. Dx dt is 5 feet per second, dy dt when x is 40 feet. Well, again, we have a small and large triangles. Next, right. If you look at this one or this one, doesn't matter. This one, this small one, and this large one, the two triangles are similar. I hope everybody knows why, because their corresponding angles are identical. This is in common. This is 90 degrees, so is this one, which makes those two identical. So those are similar figures, and again, we can pick a value from the small one and compare it to the large one. For example, this one compared to this one, or you can say from this drawing. So this is 6, this is 15. And if we want to compare this one to the large one is y. This one, I hope you see that this distance is what? Y. So this distance is y minus x. Y minus x. And that's a key, understanding similar figures, how they work. And so all we have to do the cross product. So the whole thing ends up being about this equation. So 15 times y minus x equals 6 times y. So I'm going to write it at top. 15y minus 15x equals 6y. And I can move this one to the right, becomes positive. This one to the left becomes negative. We have 9y equals 15x. 9y equals 15x. Divide both sides by 9. 15 over 9 is 5/3 x. Now we are ready to differentiate. We are going to differentiate with respect to time. So the left side is dy dt equals 5/3 times dx dt. And dx dt is replaced by 5. and it becomes 25. So thirds. So we're going to replace this with 5. 25 thirds feet per second, meaning the tip of a shadow is moving at the speed of 25 thirds. That means 8 1/3 of a feet per second when he is 40 feet from the pole.